Hello everyone, welcome to lesson 512, day 2. Today what we're going to talk about, we're going to again talk about how to write an inverse of a function, so we're going to see that one more time in today's lesson. We also want to be able to take a look at the graph of two functions and determine if they represent inverses. And we want to do the same thing with the tables, right? Can I look at two tables and say, are these tables representative of inverse functions, or can I take a look at a graph and tell if they represent two inverse functions? So we're gonna see that today and kind of build off of what we learned yesterday about the graphs and the tables. All right, so let's start off with our first example here. I've got a function. It says find the inverse of the function. So no problem. So what we're going to do that is we are going to write out our instruction manual, right? So we're going to verbally describe the function and what it is doing to x, right? So what are we doing to the input here? And we want to make sure that we respect our order of operations. So we're going to start with what's inside the parentheses first, right? So if I look at x, it looks like we are subtracting 1. Okay, so I'm going to write subtract 1. Okay, and then after parentheses comes exponent, so I see an exponent of 2 here, so we are squaring, right? So then they square. If you think about it, we subtracted 1, and then we squared. And then multiplication and division would come next. So we see a multiplication by 2 right here. So I'm going to say multiply by 2. And then here for the last step, we're going to take a look at addition and subtraction. So I do see an add 5 here on the end. So I'm going to write add 5. All right, so then I'm going to create my inverse, I have to undo all the stuff that we just did, right? I took x and then I subtracted 1, squared, multiplied by 2, and then added 5. So I need to go backwards and undo all that stuff that I just did. All right, so step 1 is going to be the undoing of step 4 here. Right, so we're going to undo add 5, right? So the opposite of adding 5 is to subtract 5. So I'm going to say subtract 5. And then I'm going to work my way backwards, right? So we go this direction, not this direction, okay? So we're going to go to the multiply by 2. The opposite of multiplying by 2 is to divide by 2. There we go. And then I go back to this step, right? So then we're going to do the opposite of squaring, which is the square root. And then we're going to work our way back to the very first step and undo that one too. So the opposite of subtracting 1 is to add 1. All right, so there we go. So now this is the instruction manual for our inverse function, right? So I'm going to come over here. I'm going to make sure I use good notation. So I'm going to say f inverse of x, right? That -1 indicates an inverse. And then what I like to do is I just like to write my x over here, right? Because this is the thing we're doing stuff to, right? X represents that input. So the first thing I need to do is subtract 5. Done. And so I subtracted 5. Then it wants us to divide by 2. Done. And then it wants us to square root. Done. And then it wants us to add 1. There we go. And remember that it's important that add 1 goes outside of the square root. The other thing that I see a lot of students do is when they square root, they only square root the top instead of the entire fraction in this scenario. So be careful with what is inside of the square root and what is not. You want to make sure you get everything that you're supposed to, right? So anything that you did that came before the square root is going to end up inside, right? So the subtraction and the division will go inside of the square root since the square root came after those two steps. The add 1 came after the square root, so this will be outside of the square root. All right, so there's our inverse. We were able to successfully write an inverse function, and we could test that by creating a graph and a table of both of these to check them and see, like, do they show us inverse, do they show that inverse relationship based on what we saw in the notes yesterday? All right, so if you recall from yesterday, when we look at a table, we were able to see that when we inversed a table, all that happened was the x and the y's here, the inputs and the outputs, they flip-flop, they switch places, right? So if I look at this point, -1, 1, right? And I write that out as an ordered pair, -1, 1. The inverse would have these two things switch places, right? So we would go 1, -1. So I'd go to my second table and say, well, here, look at that. There is a 1, -1. Now that doesn't guarantee an inverse yet because that would have to be true for every single point. All right, so when I look here at 2, 3, right, so if I write that point out over here, we would have 2, 3, and if I make those flip-flop, all right, we would have 3, comma 2. So the question is, does this exist in our table over here? Well, here I have 3, right? So I have my 3, but 3 doesn't go back to 2, it goes back to 3. Right, so when I compare these 2 points right here, I see these 2 did not flip-flop correctly, so these are not inverses. Okay. And I can find further evidence, or you only need to find one point that did not do the flip-flop or did not do the exchange of input-output correctly to determine that they are not inverses. All right, so for instance, if I did this one, 0, 4, all right, 0, 4 should, if I inversed it, would go to 4, 0, should go to 4, 0, but when I look at this, 4 went to 1, not 0. So there's another issue right there. So these first 2 tables certainly do not demonstrate inverse functions because the inputs and the outputs did not switch places. Okay? So let's take a look at another table. All right, so again, we want those inputs and outputs to switch places. So I'm looking at my inputs here. I got 1, 2, 3, 4. And 0, 2, 4, 6. Okay, so 1 went to 0, 2 went to 2. So in the inverse, 0 would go to 1. Right, so if I wrote this out, we would say 1, 0. And then those would exchange places to become 0, 1. Right, that's what we saw in the tables from yesterday's lesson. And 0, 1 is right here. So we see that first point. All right, then we'd go here to 2, 2. Right, and when they're the same number, it's kind of like, okay, obviously they're going to flip-flop to 2, 2. So do we see a 2, 2 over here? And we do. All right, so we got those. We'd go to 3, 4. All right, so 3, 4, when the input and output switch place, would become 4, comma 3. All right, and we see a 4, 3 here. And something that throws off students is that it's not in the same order, right? If we have 1, 0 here, we would expect to see the 0, 1 happen here on the same line, but it's not necessary for them to line up. The tables that they give you will sometimes be out of order. It doesn't really matter what order they present the points to you in, as long as each point over here, the inputs and outputs switch places over here. It doesn't matter what order they go in. All right, so our last one here, 4, 6, would switch places to become 6, 4. So we do see that in the second table. So this would indicate inverses based on what we can see. Okay, so you do have to remember functions do extend infinitely. So based on what I see here from these 4 points that they gave me, I would say they're probably inverses. I can't tell you for sure because I'd have to look at all the points. Okay, so these are inverses. All right, let's keep going here. So we've got some graphs, right? So we want to be able to do the same thing with graphs. So remember what we learned about graphs yesterday. When we graphed the original function and its inverse, we noticed that it had symmetry about this line, y equals x. Okay, so if they were inverses, they should be a perfect reflection over this line. All right, so when we look at these graphs, we're looking for a reflection over this green dashed line that runs diagonally from bottom to top, left to right, right? It's y equals x. So let's take a look at some of these. Now this one, I do not think this one represents an inverse. I do not see a perfect reflection. You'll notice that it's kind of off here. Typically when we see that reflection happen correctly about this line of reflection will run through this intersection point of the two functions, right? So we have this function, the red function and the blue function. If this were symmetrical, this line would be cutting this angle created here in half, right? It would be passing through this point of intersection, okay? And it is not, right? So when I graph the line y equals x, it did not pass through these two functions in a way that would represent a reflection, right? So these are not inverses. Lines can be difficult to see sometimes. So I want to show you on Desmos here, I'm going to show you this graph. So this is typically what a reflection or a symmetry about the line y equals x would look like. So I have my red function and my blue function, and this is the line y equals x right here. And you'll notice, right, it passes right through that point of intersection, and it seems to split this angle that's created right here. It seems to split that in half as it continues on. All right, so that way if I were to take everything that's on this side of that dash green line and I were to mirror it over to the other side, it would land right on top of what's on the other side. Okay, so this is a demonstration of what symmetry looks like for two lines. And when we go back to our lesson, this would be a demonstration of what it doesn't look like. That line does not pass through the point of intersection. Okay, now let's go over here. This one is looking like an inverse, right? It seems to split those two functions right in half. It's passing through the points of intersection with the functions. And if I could visualize that mirroring going over that green dashed line, what we would see above the line would land after I reflect it right on top of what's below the line. So this represents an inverse. Okay. So over here, same thing, right? I have my red function and blue function, and it's the same line. You'll notice it's the same line of reflection every single time. Okay, so this line is y equals x. And if I were to take this red function and mirror it over that green dashed line, it would land right on top of the blue function. Okay, now there's no point of intersection to see here between these two functions, which is okay. We don't always have a point of intersection to help us with visualizing that symmetry, which is why I included this particular graph. All right, so it's important to see one that doesn't have that point of intersection. So this one still has symmetry, which would indicate that these are inverses of each other. Okay. Now, when we provide reasoning, if I ever give you a graph like on a test or a quiz and I ask you, are these inverses and why? Talk about that line of symmetry. Tell me something about the line y equals x, right? So you can say these are not inverses because, and you would say they do not have symmetry about the line y equals x. Okay, so something like that is I need to know that you understand that this line of symmetry has to exist when we have the original function and its inverse on the same graph. All right, guys, one more problem here and then we'll call it a day. So in this one, we have two tables. The question is whether or not they are inverses of each other. So let's test it out. So we have this table 1, -1, right? So if that flip-flop, that'd become -1, 1, and I see that point right here. 3, -5 would flip-flop to become -5, 3. So I see it right here. This would become -9, 5. There it is. So it looks like it's almost in order as like maybe they went backwards here. So 0, 1 becomes 1, 0. -2, 5 becomes 5, -2. And -4, 9 would become 9, -4. So I see all of my points over here exchanging places. The inputs and outputs are exchanging places and creating my table over here. So, right. So how do I know using tables? I would say yes. Okay. And then it's asking us to graph both tables, and they want to know are the graphs inverses of each other. So based on what we're seeing in the table, we should see an inverse when we get to the graph. So let's focus on graphing this one first. So I'm going to go 1, -1, plot a point. So just plot the points that are in the table. 1, 2, 3, and then we're going to go down 5. So 1, 2, 3, 4, 5. Then we got 5, -9, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. It formed a line. So I'm going to grab my line tool. I'm going to draw a nice straight line through those points. Okay, so I got my line graph there, and then I'm going to change colors here. I'm going to graph the inverse table that I have. So let's do that one in blue. See what it looks like. All right, so we're going to have 9, -4. So I'm going to go right 9, down 4. All right, so we see another line kind of forming right here. So I'm going to go ahead and grab my line tool again and plot a line. All right, so there we go. So now we see our two lines graphed. Now to determine whether or not these represent inverses of each other, we have to see that symmetry about the line y equals x. So I'm going to change colors again. I'm going to go to green this time, and I'm going to grab my line tool, and I'm going to plot the line y equals x. All right, there we go. So I got my line graphed. And I would say, yep, I certainly see symmetry, right? So if I took this V shape right here, right, this is what we're looking at. This is what we would say is above the line per se. And if I were to fold that over this green line, right, fold that over or reflect it over, this V would land right on top of this V down here. So I do see that symmetry going on. So according to the graphs and according to the tables, what we see is that they are inverses. So are they? Yes, they are, based on what I see, and I know because I see symmetry on the line y equals x. There we go. All right, guys, that's it for today's lesson. Hopefully you found that helpful. Let me know if you have any questions in the Zoom chat. Have a great day.